So,
Okay.
hello everybody. It's my pleasure to introduce Professor Tornike Kadeishvili as the speaker of our seminar today. Professor Kadeishvili is a pioneer in algebraic geometry, topology, and homological algebra. 43 years ago, he published a paper, Homology of Fiber Space, where he introduced first the methods that the homotopy transfer, right? But that time the name that did not exist. The name homotopy transfer technique is only invented later. But Professor Kadeishvili invented this method, and using this method technique, he equipped the infinity structure, A infinity, and the later one, C infinity, and everything infinity structure to topological space. And yes, and since then he published many papers advancing the fields much further. And today he speaks the state of the field, yes, and the latest advancements. Please.
Thank you very much. Thank you very much. Let me start.
Yes, let us start.
It will be the general, let's say, talk about various types of, let's say, such a up to homotopy or infinity algebraic structure. Let me start with a short introduction. What is algebraic topology? Algebraic topology assigns to topological space X, which is completely complicated geometric topological object with holes, caves, I don't know, many things. And instead of it, to consider its model. Model normally is algebraic model, and it is homology group or cohomology group or homotopy group and so on. There are plenty of different models, and all models must be topologically or homotopically invariant. If X and Y are equivalent, either topologically or homotopically, then their models must be isomorphic. But if models are isomorphic, then sorry, it does not imply equivalence of starting geometrical object. Geometrical object is a complicated thing. And if you want to replace this complicated thing with easy algebraic object, you step from complicated thing to easy thing, and for this you must pay. Nobody comes without payment, and the payment is losing the information. And so isomorphism of models does not give equivalence of spaces. In history, very first topological model was Euler characteristic. Vertices minus edges plus faces. It was a single number. After some years, Betti numbers were introduced, which is not one single number, as in Euler's case, but the sequence of numbers. Each one describes its dimensional wholes. And previous Euler is the alternating sum of Betti numbers. Next was discovered by Henri Poincaré at the beginning of 20th century. It was homology groups, and homology groups are connected with Betti numbers. Betti numbers are ranks of these groups. Next, it was 30s of 20th century, cohomology, but algebra, together with multiplication. So it is more complicated object. It is not just a abelian group, but it is a ring, let's say. And that's why each next model carries more and more information. It can distinguish more and more spaces. Later, this story continued, and people were introducing in 40s and 50s Steenrod squares, massey operations, and so on. Algebraization of cohomology continues during whole century. But none of them are complete invariants. Again, one more view of this general observation. 2x topological spaces, space where correspond to its chain complex with the differential, and then chain complex has its homology. But if we, instead of chain complex, we step to co-chain complex, we come to cohomology, and cohomology, co-chain complex is more rich guy. It has a multiplication, and it indices the multiplication in cohomology. So cohomology is more rich algebraic structure. So it is more powerful than cohomology module. It is the story how algebra changes during, let's say, 20th century. In the 19th century, algebraic object was 1C, abelian group or something else, module or whatever. Yes, but after some years, they described that only one object is not enough. Collection of such algebraic objects are more essential. And this is called not just one module, but graded module. It has a gradation, numbering 0, 7. It's a collection. After a couple of years, it was discovered, but not graded, but differential graded is more important. So there are such a maps, differentials with condition dd equals to 0. dd equals to 0. And the image of D is denoted by boundaries. Kernel of D is called cycles, and the condition dd equals to 0 implies that the B is part of Z. So we can factor, and factor is homology. Henri Poincaré, beginning of 20th century. If we consider collection of C's, but when differential goes not from right to left, but from left to right, then it is called co-chain complex, and its homology are called cohomology groups. Whenever someone, Henri Poincaré, introduces a new type of object, it was said very after 50 years by Eilenberg and MacLean, we must introduce immediately the morphism. But morphisms are such a collection of homomorphisms so that each diagram commutes. Each diagram commutes, it's called chain map. Then commuting of diagram implies that Z's cycles go to cycles and B's boundaries go to boundaries. So they produce the correct map of homologies. So homology is a functor, chain map. Instead of chain map, it is old-fashioned name, differential graded module, let's say, differential graded module. It is collection with differentials and dd equals to 0. Now I have erased differential module and replaced by the word differential graded algebra. We have this, if we have in this object the big graded thing, multiplication, but it is not so like the each C is a abelian group. Each C is a ring. No, multiplication is of this type, p-dimensional A times q-dimensional B, and the result is p plus q-dimensional. This product, this, and it jumps somewhere. This is differential graded algebra, but it must be connected with differential. And sorry for this D, I should use the same D. DAB is DAB plus ADB. Hey, this is the clear story about derivatives, yes? Derivative of product of two functions is the same formula. And we have nothing to do with derivatives here, with this Leibniz rule. But maybe that is why this, another name of this is not a differential, but border operator. Geometrically, it is the border of something. But since this border operator has the same property as real calculus differential, Leibniz rule, they call it also differential. And we have a chain map, and it induces correct multiplication in homology. Correct multiplication mu star. Mu was that strange summing dimension multiplication of C's. Mu star is again summing dimension multiplication of homologies. And this follows from Leibniz rule. Leibniz, not calculus rule, but used in our case. Morphism of differential algebras is morphism which it makes not only commutative diagrams, but it keeps the product and it induces. And now let me formulate, one knows it very well, main goal. Take a C, chain complex, D, and it has homology. Here, homology. Homology is just graded object. It has only collection. But I put here arrow 0, arrow 0. Consider homology not only the collection, but it's a chain complex with trivial differential. What will be the homology of with this trivial chain complex? H itself. Cohomology of C's, HH. So this complex and this complex, they have same homologies. Oh my God, how wonderful it is. C is terribly big, especially, for example, if it is simply shield chain complex or whatever. But H is very, very small, and it is dream of all topologies to replace these terribly complicated C's by easy H's. But it is economical principle. If you step from something complicated to something easier, it costs money. You must pay for it. It is, you lose the information. collection of H's or chain complex with zero differentials. That it has the same homology as C's, but it is not so informative. You see why? We can easily construct a chain map to each element of homology. It is equivalence class factor. Choose a cycle. Cycle choosing, cycle choosing, cycle choosing. We choose cycles. And easy to see that diagram is commutative. So a diagram is, this is a chain map. Maybe this indices isomorphism in homology. Homologies are isomorphic, but is it indexed by map? No, unfortunately, this is not multiplicative. Cycle choosing from product is not the product of chosen cycles. This is the grandiose tragedy of this story. Homology, C are they have the same homology, but this isomorphism of homology is not induced by normal map. Let me mention also one more thing. We had here differential graded algebra. And what was algebra? Algebra was the product C to C. And coalgebra is it is a little bit sadistic thing from category theorists to invert all arrows. Invert this multiplication, and we obtain co-multiplication. And this object with multiplication is called algebra, but with co-multiplication is called coalgebra. And time to time, we need more, often coalgebra stories, but everything about coalgebra can be obtained from algebra, inverting arrows. For example, associativity, it is ABC equals to ABC of red algebra. What is associativity of diagonal coalgebra? It is not easy to write it this way, but this is commutativity of this diagram. And Leibniz rule also can be replaced by its dual formula. So we have differential algebras. It is chain complex C, D, and mu multiplication. And it's dual C, D, and delta diagonal, let's say, the co-multiplication. Okay. Whoa, it takes much more time than I expected. Bar and Kobar factors. I want to describe very popular Bar and Kobar factors by Eilenberg and MacLean. And these are dual things. Two DG algebras corresponds its B, bar construction, which is DG coalgebra, and by omega cobar construction corresponds to the bar, cobar, cobar, dualism. What does it mean? First of all, I need the co-free algebra and co-free coalgebra. Let me take R, let it be our ground ring, and V be some module or vector space or abelian group or whatever. Take this collection, V, and so on. And this is called tensor algebra. I'll show you what is algebra here, how to multiply. And also, the same thing, it is not the usual story. Algebra and coalgebra normally are different, but it is an exception. In this case, the same object plays the role of free algebra and co-free coalgebra, tensor coalgebra. Now, multiplication, why it is algebra? Let us take one element from here, from somewhere. Somewhere is the word consisting of A1, A2, AM, another word, AM plus 1, AM plus N, and their product is just put them together, long M plus N word. Such a natural, very natural multiplication. Dualizing it, we have what is product from 1, 2, and corresponds 1. But what is co-product, the diagonal to 1 corresponds 2. 2 to 1 multiplication, 1 to 2 co-multiplication. And co-diagonal, the delta of A1, AN is a sum of, I'm cutting somewhere, 2 parts, somewhere, 2 parts, somewhere, 2 parts, and such a sum is a co-multiplication. This is free algebra. Why doesn't? And this is free coalgebra. Why to jumping? What does it mean free? Why TV is a free object? Free means that free generated by V. If I take some map from generators to some other algebra, any alpha, to it corresponds not any map, but almost honest algebra, multiplicative map, F alpha, with this condition, F of product is Fx, F of y. And this is the formula how alpha defines F alpha. Same story. Something is wrong in my pictures. Same story for tensor coalgebra. Tensor coalgebra is here V is generators, and any map on generator can be transported as an honest algebra map. Here, any map from any coalgebra to alpha can be transported to coalgebra map. And here is the formula. I don't want you to waste time on it. And when we speak about differential story, in the world of algebra, they are not only multiplicative map. F of product is product of F's. There are also derivations, and the free object is free not with respect to algebra maps, but also for derivation. And what is derivation? What Newton and Leibniz wanted. The derivative of product is derivative of x times y, x of times dy. And there is a standard way when derivative is given on generators to enlarge it, to continue it on whole TV as a algebra map, and the same story for dualism. What happened? I don't know. And this tensor algebra and tensor coalgebra, they will play the role of bar construction and co-bar construction by Eilenberg and MacLean. What is Start with coalgebra. Coalgebra has a differential and diagonal, 1, 2, 2. And its cobar construction is produce the tensor algebra. It is algebra, yes, no. But differential in tensor algebra is a D travels and nabla also travels. Dualize everything. What is differential in the bar construction? If I had algebra, I produce a coalgebra TC, and this will be the bar construction of A with differential dA, which is D travels in, or neighbors are multiplied. And the same story for coderivations. Oh, what shall I do? Let me concentrate on bar construction. Suppose I have DG algebra A. Its bar construction is tensor coalgebra, and it is a co-free object. If I take for free object any map from generators, no, any map from tensor coalgebra to co-generators can be enlarged to a differential. And the differential is given by beta. And what is beta? What is tensor coalgebra? It is V. So beta is beta 1. It is from V to V. Beta 2 from V tensor V to V. Beta 3, and so on. Such an infinite collection of components has beta, and it can be enlarged to a differential d beta. But look at it. In a real classical bar construction, work only beta 1 and beta 2. Beta 1 and beta 2, all others are 0. That is why, because our A was algebra. Algebra had only differential and product, but not the triple product and such a things. But who said that? It was my wonderful discovery. I am explaining it to children when I am lecturing in the school. Arithmetic or algebraic operations are binary. Binary means they have, binary means, I'm sorry. It is like a, for example, the multiplicative operation. It is such a box that you have 2 inputs and 1 output. If inputs are numbers 2 and 3, their multiplication is 6. So is summation binary. But who said that we must have always, for arithmetic operations, 2 inputs? Maybe 3 inputs or 4 inputs, 5 inputs. More informative algebraic operations. This was done by James Tashet. B1 is 1 argument operation. Unar, I don't know whether there exists such a word, binar, ternar, and quaternar, and so on. And Stashev's algebra, why don't us take any B1, B2, B3, and so on to continue it as a derivation? But what guarantees dB equals to 0? Idea was not only binary operation. Here we have in standard situation unar operation and binary operation, and all others are 0. But our wish is to introduce operation with many. And the same story for what we did in previous. Any beta we have enlarged as a differential. Now I want where I am. Sorry. Beta. First time see I saw such a tragedy. No, it goes to bed. And also, I want to do the following. Not only differential induced by beta, but I need also tensor coalgebra is coalgebra from 1 to 2. But I need here the product from 2 to 1. And this must be algebra map. It must be induced by E. What is E? What is TC? It is 1V, 5V, 7V. What is another TCV? It is 5V second. And E is such a collection. I read it, I put it like Pascal's triangle. What is E? 2, 3. It is V tensor V, first argument, and V, second argument. So if we need a multiplication, we need this crazy amount of triangle of all such a products. Instead of beta 1, beta 2, beta 3, here we have such a pyramid or triangle, if we want to it. Now I step to infinity algebras. And half an hour and 35 minutes. But when I controlled my lecture at home, it took only 20 hours. I'm afraid I do not manage. What is infinity algebra? Remember this when I want a differential in tensor coalgebra in bar construction, I need a beta. And beta was a collection. And it is a good step to Stashev's infinity algebra. It was discovered in the beginning of 60s. And Stashev's aim was absolutely different. The infinity algebra was introduced by homotopical reasons. It was not prepared to be used in algebraic situation. Jim Stashev. And Jim Stashev played the great role in my life. You see, I'm from Soviet Union. Many of you are from Czechoslovakia, and the situation was less contacts with Western colleagues, and all papers were printed in Russian, yes, and but I was so happy that my paper in 80 was printed in Успехи математических наук, and it is translated to United States. It is called Russian Mathematics Surveys. But I am not Russian, I'm Georgian. My paper appeared in Russian Mathematics Surveys, and Stashev has seen it. And then after a couple of years, he sent me a letter that he likes it very much, and he popularized this my paper, and that's why I made a step to Western mathematics. It was almost impossible in communistic time. Maybe one knows more or less this. But now it is, no, now it is free. Now it is open. So Stashev's infinity algebra. It is some M collection, MK, graded object, with the sequence of operations. M1, which is M to M, M2, M tensor M to M, like multiplication, M3, triple multiplication, and so on. But Stashev also assumed this property. You see, M, and inside the red M runs inside of it, and the red M's length, J, also changes. Quite clever but complicated condition. But it is always very good to look it in low dimensions. M1 is from M to M, M2, MM to M, M3, MM to M. So that, and what this, I rewrote this Stashev's condition here. This, if I rewrite the condition now, it will be M1 equals to 0. Oh, M1 is differential. Next condition is M1, M2, M2, M1, M2, M1. But it is the same as differential or product is D1, DA, DA2, and A2, D. So what is it? It is Leibniz rule. So M1 is differential, M2 is Leibniz. And the grandiose thing, it is about Stashev's condition about M3. Look only to blue part. Blue part is a product, and then this product produced with M3. Oh, and here is first A2, A3, and then only N1. So blue part is associativity. ABC equals to ABC. But it is not 0. It is 0 after adding the red part. And what is the red part? It is differential M1 of M3, and then M3 on N1 in E. So it is M2 is associative. Just to M2 is associative, but not correctly associative, up to homotopy. So A is not 0. It is differential of M3 and M3 of differential. So differentiability, that is why another name of Stashev's infinity algebra is SHA, strong homotopy associative. Why homotopy associative? Because M1 is classical differential, M2 is classical algebra, M3 is something new. What is new is in M3? M3 is a homotopy which measures deviation from associativity. But it's not only. There comes also M4, M5, and that's why here stands S, strong homotopy associativity. Homotopy associativity, there will be M1, M2, M3 only, but it is not enough. And the higher orders also show up. And the stashes, and then how we can use these operations? Hey, we can write a new differential in tensor coalgebra. It is differential M, depending on this collection M1, M2, M3, and so on. dm on some collection A1, A2, N is a operation M travels inside of it. And the Stashev's fancy condition guarantees exactly dm equals to 0. And this is called bar construction of M, but it is not bar construction of classical, but A infinity. So bar tilde is such a notation. There is also morphism of A infinity algebra. What is morphism of usual algebras? It is a chain map which is connected to M1 and with M2, multiplicative. But here we have M3, M4, M3, M4. What to do? Stashev did not have this morphism notion, and I did it in 75 when I was a PhD student, by the way. It is something with some properties, and these properties guarantee that it is strong homotopy multiplicative map, and it guarantees that it is correct map of corresponding bar constructions. Bar constructions. For any infinity algebras and morphism, if I leave only M1, M1, and F1, we are in classical chain map. It is chain complex only with one differential, chain complex and chain map. So weak equivalent, if this first component chain map is homology isomorphism. And we call infinity algebra minimal if M1 equals to 0. And any minimal weak equivalence in isomorphism, or forget about it. If I have infinity algebra with only 2 operations and all others are 0, hey, then it is our good old friend, differential algebra. Differential algebra. So category of differential algebras is subcategory, and bar tilde construction of such 0, 0, 0 is the same as normal Maclaurin bar construction. And the morphism is normal morphism. So there is such a diagram of categories. DG algebras is a subcategory of infinity algebras. DG algebras are infinity algebras with only first 2 operations. And bar construction, the bar tilde coincide in this case, such a. And now let me tell you about my minimality theorem, which was in that paper which discovered Stashev, and Stashev reported it to Western mathematicians. Otherwise, it was in Russian language, and it was only for Soviets. Remember our story, C and HC. C is differential algebra with differential M1 and let it be M2, not mu. And minimality theorem shows that there is inductive method to produce here not only M1 equals to 0 and M2 is multiplication in Dustin homology, but they appear also M3, M4, and so on. And homology equipped with M1, M2, M3, M4, and so is exactly as informative as a starting chain complex. So when we stepped from chain complex to its homology algebra, we said that we are losing plenty of informations. But if we add to cohomology collection of all MEs, then it carries the same information as our chi. And this is not uniquely determined. There is some freedom. One knows it, but this freedom is guaranteed up to isomorphism, and there is some sort of factoriality. This minimality theorem, transporting X infinity algebra to homology. X I put for not only for only I infinity. The outer Stashev appeared plenty of different infinities. These are what? What are our algebras? Normal algebra is with multiplication. Multiplication must be associative. And what will be non-associative? In good case, it will be strong homotopy associative. It is infinity. It is a Lie algebra. Lie algebra also has a binder operation. And what is the name of condition which guarantees that it is Lie? We see condition, the ABC. Hey, Van, what condition of Lie algebra?
The algebra is, of course, that's how to say, Jakobi
Jakobi
operator.
identity.
Jakobi, yes.
Yeah.
And if we have Lie algebra, but not Lie algebra, with some brace operation, but it is not Jakobi, but it is Jakobi up to homotopy. It will be 3 Lie. Then comes 4 Lie, 5 Lie, and L infinity. Here comes also C infinity. It is a commutative version of A infinity. Commutative version of A infinity. I'm not sure I should manage to cover today, but it is very informative. It determines homotopy type in rational case. And what is here? C infinity, I did in 88. Mark, which is your Mark from your institute. Is he in this room?
I don't think Martin is here. So
Mark was involved here. In L infinity, Martin made this minimality theorem, transporting from normal Lie algebra to homology of Lie algebra. But L infinity, it was Tom Lada and Martin Mark. Hubschmann and Stashev also did it. Kontsevich and Zoiberman did it. And they used in some factorization problem in physics. Then Kenji Fukaya did something grandiose. A infinity, not algebras, but A infinity categories, infinity categories. Infinity algebra is, from category point of view, one object, and its endomorphisms are our differential algebra. But Kenji Fukaya, the generalized infinity notion of infinity to category story, and proved this my minimality theorem to this situation. And using this, he proved the mirror symmetry problem. This is a great problem in physics, which speaks what is our higher dimensions. Our world is not 3 or 4 dimensionals, it is 11 dimensionals by string theory, and from 5 to 11 there are 6 extra dimensions, and these extra dimensions are quite complicated topological spaces with very terrible holes and caves and many such things, and its topology is needed to know. And Fukaya catched how to calculate this homology, let's say this. It is not known which 6-dimensional manifolds are in reality our extra dimensions. There are several 1,000 candidates to be extra dimensions, and Kenji Fukaya proved that to each extra dimensional manifold corresponds its infinity free minimal theorem, minimal model, and the 2 of them produce the same physics if their infinity models are the same. This is such a story. I don't want to waste much time. First, new operation, it is easy to describe, but fancy thing is, in mathematics, there exists such a fancy thing that is massy product. Massy product is a triple product of 3 elements, A, B, C, in algebraic places, but it is not always defined. It is defined only when AB equals to 0 and BC equals to 0. Not all triples, but for some triples, and it is not uniquely determined. So it is a set. And I have shown that my operation M3 from my minimality theorem is an element from massy product. And it was a grandiose thing, because there are plenty of wonderful, nicest examples of topological spaces with non-zero massy products. As I said, massy product is not one element, it's a set. And non-zero means this set does not contain 0. So if my operation is in this set, it means that my operation is not 0. It gives plenty of examples of non-zero infinity algebra structure. There is one strange thing. Another name of infinity algebra was strong homotopy associated. Operation M3 was measuring, operation M3 was measuring non-associativity. But here it appears in homology, and it is strictly associative. So it is strictly associative. It is nothing to measure with operation M3 and so on, because there is no need to measure non-associativity because it is associative. Strange thing is that although there is no need to measure non-associativity because the starting object is strictly associative, Nevertheless, there exists non-trivial this measuring operation M3. So I show you this picture. I finished this story with this picture. I love this to show to my students everything, not by speaking, not by formulas, but by pictures. We discussed it. We have differential algebra, C, D product, homology in dot product. But unfortunately, there exists, both of them have same homologies, but it is not induced by some map. So they are not equivalent chain complexes because this cycle choosing is not preserving multiplication, is not multiplicative. So there exists no isomorphism between bar construction of C and bar construction of its good friend HC. But if we somehow change differential in bar construction, dB plus some H, then they are equivalent with some F. But what does it mean, changing differential? Changing differential, it is the collection M3, M4, M5, and such a map of corresponding infinities. This is the picture which shows us the last thing. So our aim is that if we have differential algebra, in its homology appears an infinity. What is differential algebra? Differential algebra is co-chain complex of topological space. In it appears an infinity, and bar construction of H and bar construction of C, they have same homologies. But it is classical result of Adams that bar construction of C gives homology of loop space. So if I take bar construction of homology only, it does not give homology of loop space. But if I equip with these infinity operations and do the bar tilde construction, then I catch the loop space. And the same story if I have a group, and it is not interesting. I add some word here because I have one more minute. It is very interesting when these higher operations, M2 remains, but M3, M4, M5, and so on, disappear. So when infinity algebra is degenerate, it is simple algebra. It is there is a special obstruction theory, and the obstructions are in Hochschild homologies, which is absolutely different part of mathematics. And from first of view, it has nothing to do with topology, Hochschild homology, Hochschild cohomology. But so there is obstruction for degeneracy, and obstructions lay in Hochschild cohomologies. And then the next is whole theory of Hochschild cohomologies, but I want to leave it, and then it comes something called C infinity, which has the application is rational homotopy. Then I step to bar constructions and rationals, but I have no time for it. See, when I'm speaking with my students, I'm warning them that never make a talk with more than 20 slides in slideshow, and see how many I prepared. exactly 200. But let me stop here. Let me stop here. Hey, because there is no chance to. Where are you, Juan?
Yes, that means that you still no, just stop. You can speak some 10 minutes more because I think that it should be some homotopy chess and algebra is very interesting. And I didn't know anything about, I mean, that you wrote something about that.
About what you said? Homotopy.
I mean, yes, there should be you encode homotopy class of the C infinity structure or infinity structure using
okay,
the
okay.
thing. Yes.
Okay, very shortly. We had the notion of infinity algebras. We had the notion of infinity algebras. Oh, moment. We have the notion of infinity algebra. But infinity algebras are differentials in tensor coalgebra. But in tensor what? Why stands here C? Tensor coalgebra. There is also tensor algebra, but tensor algebra and tensor coalgebra standard free maps are not connected to each other. They do not form the B algebra. But there exists so-called shuffle product. Shuffle product. It is very funny explanation of shuffle product, like playing the cards. There are black cards, cross and what? I don't remember English names. And heart and something, red cards. Suppose I have black cards and red cards. Black cards and red cards. And I shuffle them. Red cards keep their order. Black cards keep their order. But totally is something shuffled. Or I shuffle by another way, but only once. Shuffle. For example, what a shuffle product of one black, red card and one black. It is A, B, B, A, nothing interesting. A and shuffle product with BC. BC is a two cards, B and C, and they keep their order. A, B, C, B, C, B, A, C, B, C, A. What is A, B? Two black cards, Karol Idama, saying in Russian. And two red cards, it is when A and B are close to each other, such a shuffles. A, B, C, D, C, A, B, C, D, A, B. But then also when distance between A and B is more. A, B, C, D, C, A, D, B. See, reds keep their order. Blacks keep their order. And the last one, A, B, distance big, but all of them keep the order. And commutative infinity algebra is infinity algebra with each operation disappears, dies on shuffles. M2 AB plus M2 BA. Hey, you mentioned that I ignore all the time signs. Signs, because there is a standard way. Who is this French mathematician who discovered this method? You can always correct the signs, yes, if you work with graded situation. M2 is commutative, if I send it. M3 ABC, M3 BA, M3 ABC 0, M4 . So commutative infinity algebra is such infinity algebra. And what is good in infinity algebra is that the bar construction is, with respect to shuffle product, bar construction was tensor coalgebra, but now it is also algebra. So it is Hopf algebra. It has multiplication and co-multiplication simultaneously. And obstructions in Harrison, Arminda. Minimality theorem. If the starting differential algebra is commutative, then the infinity structure, which appeared by the previous minimality theorem, is not infinity only, it is C-infinity. It is C-infinity. And yes, and A, in the middle of 70s, Dennis Sullivan introduced his rational homotopy theory. Whole day I am talking that topology is complicated. Its algebraic model is easy. But it is no way to produce algebraic model which is so rich that it carries full information about starting topological space. But in Sullivan's case, in a rational case, Sullivan's commutative model was complete. In this rational case, it is big restriction, rationality, but there exists complete algebraic model. And what about our theorem? If I take Sullivan's commutative cochains, normal cochains are not commutative, but Sullivan's cochains are commutative, then appear cohomology in C-infinity in what? Cohomology of X with coefficients in Q, rational numbers. Rational numbers. We're discussing this today. And there exist several complete describing everything in rational case. Before Sullivan, some years before, Quillen managed to produce the Lie algebra, which describes, then Sullivan itself in 75, I think, Halperin and our friend Stashev, and also what I'm saying now, cohomology equipped with a C-infinity. It is complete topological invariance. Why so? Two topological spaces, X and Y, rational spaces, are equivalent if they are AX and AY, chain level, are weak equivalent. But they are weak equivalent if their homologies are C-infinity equivalent. Trivial result. Trivially follows from Sullivan's. And so it determines rational homotopy type. Even more, if I have a cohomology algebra, some algebra, and I consider all possible spaces whose rational cohomology is given algebra, and factor it by rational homotopy equivalences, it is bijective to all possible C-infinity algebra structures. Formality. When Stashev defines formal space such that its cohomology and its cochain are equivalent. Cohomology, it means in my terminology that its infinity structure is zero. All operations are zero. Where are the obstructions for formality? In Harrison cohomology. And many things can do. When we have in our hand complete invariant, we can speak about when a algebraic homomorphism between cohomologies is realizable as a continuous map when it is extendable as a C-infinity morphism. And we can calculate also rational homotopy groups. We take a bar construction. Bar construction now is not only co-algebra, but algebra. Algebra has non-divisible elements, Q elements, and homotopy is homology of non-divisible elements. This is complete invariant. Complete invariant. I have seen in the last years appeared, I don't remember the name, one, let's say, most philosophical work of someone. In a rational case, there exists complete invariance. Yes, coherence, and mine. But outside, as you love Z and Z4, of course, there is no chance. No, there is. If I consider the opera, some very, very general operate, which has quite some technical description, but another philosophical description is the operate consisting all by all functorial operations. And this operad action is complete invariant outside of rational. But nobody can observe what is this operad. Okay, let me finish. Thank you very much.
Yes, thank you very much.
And sorry that I did not finish. I
Yes,
speak
but that is very
only A and
exciting
C.
lecture.
I missed homology, Gerstenhaber algebras.
Yes, and that is a question. That is, of course, very interesting. So maybe you can.
I send you this my 200
Yes,
slideshow, and you can.
So I just
see.
ask you on the question, of course, maybe more, but first, what is the advantage of C-infinity algebra over Sullivan or Quillen or Hilbert Starship?
No. I don't know what is this. No. Sullivan's model is chain complex.
Yes. Yes, chain complex, and he has to.
Chain complex, and chain complex is big, but homology is small. What is better to know, to describe, to explain to computer, calculate something for this chain complex, which maybe it will be infinite in dimensions. But homology of sphere is in dimension 0 and in dimension n, and that's it. But Sullivan's cochains are in all dimensions, some says. As an object to play with it. Homology is much smaller. Maybe this is advantage. Yes, Hilbert and Stashev also, they had some resolutions, so they are big objects. Quillen also is big object, but this is small.
I have a very basic question. You know that there are these curly algebras and curly categories, namely in the A-infinity case, what I mean is non-triviality of mu0, right? Do you have, or is there a version of this minimality theorem for these curly algebras or curly categories?
Wow. I didn't hear Galovka.
Can you hear me now? I can say it again. So
you speak a little bit slower.
Please speak slowly and clearly.
Okay, so there is a notion of curly A-infinity algebra and curly A-infinity category, where there is also mu0 operation. So my question is, if mu0 is non-trivial, namely, if there are this like curly algebras or curly categories, is there a version of minimality theorem?
Whoa. I did not understand what you said, and I did not understand what you are speaking about. Maybe I don't know what is this.
So Roman, I was missed. So you're speaking about the which situations?
I was speaking about situation when there is mu0. So zeros operation, zeros a infinity operation, which is non-trivial. So there is a notion of curly algebras, curly a infinity algebras.
So you have
do you mean? So
only
Roman, do you mean
one
curved?
and 2. What is zero operations?
Some people say curves. I think so. I know that notion curly, maybe curved is another. Yeah, it's equivalent.
What is what he pronounces? What?
Curved or curly.
Once again, there is mu0, non-trivial mu0.
Infinity algebra, but we can with you mean the curve.
Triviality of infinity algebra means zeroity of operations.
Yes, that means I see. That mean d square not necessarily.
Formality means only M2 operation exists, and the higher all are zero.
So the notion of the curve, that means that d square not necessarily equal 0, you mean, Roman?
Yes, exactly.
Yes.
So d square is not necessarily 0. Yes.
Do you consider such a curve C infinity or infinity and infinity algebra? Curve, yeah. So I write a curve. Curve. Infinity structure. Yes. So did you consider, or maybe Professor Kadeishvili, did you consider curve infinity structure?
No.
No, yeah.
I have heard, but I don't know.
So there is no hope to get like a version of minimality theorem for this curly.
Curve theory, yes. So, so you are talking about the infinity structure for curve theory. So can you?
So far for all infinity, A, C, B, people prove minimality theorems. Hopefully, maybe it appears there. From L infinity also there exists minimality theorem. I can't say which.
Yes. Roman, I also remember to math is the curve structure somewhere, but why do you interested in such structure? I forgot.
Because at least from the point of view of hGa categories, this appears, so this type of structures, they appear in the obstructed situation. When, let's say, if you consider the Lagrangian model,
yes,
you could potentially have some holomorphic disks that don't allow you to get disk work, but you still have a infinity structure.
Yes.
Can I ask a question?
Yes, is it hGa? Sure.
First, thank you for this very nice lecture. So I wanted to hear your comment about this this way that C infinity algebras capture the homotopy type, but in the case when the underlying topological space is not simply connected. So I know that this equivalence, I think, often when it's stated, it uses simple connectedness. So in the case when it's the space is not simply connected, Do you know what else is needed to capture the homotopy type, and how that transfers to this C infinity model?
Well, you see, I have nothing to do with topological spaces.
Mm-hmm.
I work with Sullivan's models.
Mm-hmm. Okay.
Oh, and Sullivan's models are totally described by their C infinity cohomologies.
Mm-hmm.
If Sullivan manages
Yes.
to enlarge his model, yes, then H follows to him. It is a question to Sullivan.
Mm-hmm. Okay, thank you.
Yes. Okay, if there are no more questions, let us thank the speaker again. Yeah.
Thank you very much. Thank you very much. It was
Yeah.
nice to see
Thank
you.
you.